Welcome, class. So today we're going to continue our look at measurements, and today I want to focus on temperature scales and look a little bit at density as an example of a complex or derived unit of measurement. So first of all, temperature, right? So we stated earlier that when we were talking about energy, the temperature was the way that we measure the thermal energy of a material. So remember, thermal energy is that kinetic energy that results from the movement of the atoms or molecules that make up a sample. And measuring the temperature gives you sort of a relative measure of the average kinetic energy of those molecules or atoms. Now, the scales or the units that are used to measure temperature, right? There's three sort of common ones, right? The oldest is the Fahrenheit scale, which we still commonly use in the U.S. And pretty much nowhere else in the world. So really it only exists because we tend to use it. There is the Celsius scale, which is the most common scale used everywhere else in the world and within the scientific community. And then, of course, there's the Kelvin scale, which we stated earlier is the SI unit for temperature. Now, we'll talk a little bit more about the Kelvin scale here in a second. So let's just briefly look at these different scales and how they're maybe similar and different to each other. So, first of all, if we compare the Fahrenheit and the Celsius scales, the first thing that we should realize is that the unit, a degree Fahrenheit, right, is a different size than a degree Celsius, right? So a degree Fahrenheit is smaller than a degree Celsius. So if we look at the difference between the freezing point and the boiling point of water, that is 180 degrees Fahrenheit within that difference, but only 100 Celsius degrees. So the Fahrenheit degrees are smaller. They're a different size. This is part of the reason why the conversion between them is a bit more challenging. You'll also notice that the Celsius scale, things were tried to be, you would use that idea of base 10, right? So the freezing point on the Celsius scale was pegged at 0, and the boiling point of water was pegged at 100, right? So we defined 100 degrees different, right? And of course, that wasn't the case on the Fahrenheit scale, right? Water freezes at 32 Fahrenheit and boiled at 212 Fahrenheit. So Fahrenheit and Celsius. Now, the last unit here is the Kelvin. Now, one nice thing about the Kelvin in regards to the Celsius scale is that a Kelvin, right, is equal to a degree Celsius, right? So the unit size is exactly the same. Now, one thing that's often sort of confused here, it is not a degree Kelvin, right? There is no degree sign in the unit. It is just a Kelvin. That is the unit. And so that's how we should express it. But the conversion between the two scales is quite a bit easier because the units are exactly the same size. So it's just a simple difference in the value. So on the Kelvin scale, water freezes at 273 Kelvin and water boils at 100 degrees higher, or 373 Kelvin. Now, why are the numbers on the Kelvin scale so much different? Well, the key is the Kelvin scale was established as an absolute scale. And all that simply means is that there are no negative values. So, the lowest possible temperature on the Kelvin scale is 0. This is what we refer to as absolute 0. Now, this is a theoretic temperature. We have not actually ever reached this temperature. We've gotten really, really, really close to this temperature, but we've never actually achieved it. But there's large support, to what, saying, where this value falls, right? And so it was established that absolute zero would fall at negative 273 Celsius, or you might see it more precisely at negative 273.15 degrees Celsius. So that automatically became 0 on the Kelvin scale, and then everything scaled with that. So what you'll notice is that at every temperature point, there is a difference of 273, or again, more properly, a difference of 273.15. So if we look at converting between Kelvin and Celsius, we can see it's a very straightforward conversion. That my temperature on the Kelvin scale is simply going to be my temperature on the Celsius plus this 273.15. So if I want to convert 353.50 Kelvin into Celsius, and then we'll do it to Fahrenheit here, this is what I need to do. So if I write this out, that 353.50 Kelvin equals degrees Celsius plus 273.15. So I can do my arithmetic, can subtract 273.15 from both sides. So I get 353.50 minus 273.15 equals, so if we plug that into our calculator here, we have 353.5 minus 273.15. We get 80.35 degrees Celsius. Right? And of course, we should always make sure our answers make sense, and it does. The Celsius temperature should always be the lower, right? If we look at the two scales, the Kelvin temperature is always the higher one by 273.15. Now, what about converting between Fahrenheit and Celsius? Well, we do have the equation here, right? And so if we want to calculate our degrees Fahrenheit here, we can take 1.8 times the Celsius temperature, so 80.35 plus 32, and that will give me the Fahrenheit. So if I plug that in, I get my 80.35 times 1.8 plus 32. We get 176.63 degrees Fahrenheit. And if we look out here, right, that might make sense. So, your 80 degrees Celsius is going to be somewhere in here, and that's going to be up here in, this region of the Fahrenheit scale. So it makes a little sense here. Your answer makes sense. But the conversion is, not as easy to do just simply in your head or very quickly, because you have to take the 1.8 accounts for the difference in size of the units, and the 32 is the fact that is the difference between the 0 points on the Celsius and the Fahrenheit scale. So these are our three temperature scales, and how we're going to work for them. But in this class, we will almost exclusively work within the Celsius and the Kelvin scales. Now, the next idea I want to talk about is a bit about a derived unit or complex unit, and the example we're going to use is density. So we'll talk specifically about density in a minute, but density is an example of what's called an intensive property. So when we talk about the physical properties, especially of a material, they can either be what we are called intensive or extensive properties sometimes. So an intensive property, like what density is, does not depend on the amount. So it's independent of the amount of material you have. So density would be an example. And so a material will have the same density regardless of whether I have a small amount of it or a large amount. Right? So a gold bar has the same density as a gold coin. Right? So density is an intensive property. Now, intensive properties are often used to identify materials. Because they don't depend on amount, they're often intrinsic to the material, right? So they can be used as ways to identify a material. Now, the contrast to that is what we call an extensive property. And as you might guess, these do depend on the amount. And so these particular properties will change with the amount of substance that you have. So examples of these might be mass or volume, right? So if I have more material, the mass is going to go up, right? More material, the volume is going to go up. So as a result, because these change with the amount, they can't be used to identify the material. So if I know what the mass of something is, that's not going to allow me to tell what it is. But if I know the density of that material, well, that may allow me to identify what the material is. So extensive properties can't be used to identify a material. Now, we're going to look at a specific example of one of these intensive properties, and that's density. Now, the reason we explore density at this point is because it's a good example of a physical property, right? One of these intensive physical properties, but it's also is an example of what we call a combined unit, right? So we have simple units like length and mass, etc., right, that we talked about. But we also have complex units, and complex units are combinations of our basic units. So density is the measure density is the measure of the mass per unit volume. Right? So it is the amount of mass that we have in a unit of volume. So the way we typically express that is we would say the density is equal to the mass of an object divided by the volume that it occupies. Which means that we commonly express it in units of mass, so grams, and then for volume, right, where volume itself is a derived or complex unit, the two basic scales for volume are going to be cubic centimeters, or typically milliliters is what we would use for densities, but that's part of the liter scale, right? So the difference here is cubic centimeters are usually used for solids. Liters or milliliters scale is used for liquids. Now, you can interchange these quite readily. Nice thing is that 1 cubic centimeter is exactly equivalent to 1 milliliter. So no matter which unit you use, it doesn't numerically affect the value. So while I could look at my table over here and say that, oh, ethanol has a density of 0.789 grams per cubic centimeter, it would also have 0.789 grams per milliliter. Right? So cubic centimeters and milliliters are nice, can be exchanged for one another quite readily. So the basic equation for density then is often abbreviated as density equals mass divided by volume. Or again, the ratio of the amount of mass per unit volume of a material. So let's do an example problem here. So let's say that we are saying that what is the density of a ring with a mass of 4.53 grams and a volume of 0.212 cubic centimeters. And we want to see if this ring is really platinum. Right? So again, being one of these intensive properties, right, this is one that we can use as an identifier, right? Because it doesn't matter how much we have of it, it's going to have the same value, right? The same ratio of mass per volume. So if I look at my equation and I want to calculate the density, I'm going to put my mass, 4.53 grams, divided by 0.212 cubic centimeters. So we got mass divided by volume. Now, when I do this on the calculator, it's going to spit out something like 21.3679. And now, the way I write the units is that's 21.379 grams per every cubic centimeter, or per every 1 cubic centimeter. Now, at this point, we need to start thinking about rounding and how many of these digits we can really show. Now, we're going to talk about this in more detail a little bit later when we talk about the concept of significant figures. But for now, let's just say it. If we look at these two numbers, they both have what we call 3 significant figures. So we have 3 significant figures here, the 4, 5, and 3 significant figures here, and the 2, 1, 2. So my answer can be rounded to 3 digits, to 3 significant figures. So that means I'm going to round it to stop here. So I look at the next number. We use traditional rounding rules. So the 6 tells me that I round this up. So this would round to 21.4 grams in every cubic centimeter. So that's the density of this ring. Now, is it platinum? Well, if I look at my table and I look up the density of platinum, I see it is indeed 21.4 grams per cubic centimeter, or grams per milliliter. So yes, we could say that this ring is made of platinum. We could be confident of that. Okay, so next time we are going to move on from talking about these ideas, and we're going to dive into what we were just mentioning there, this idea of significant figures.